Good morning and welcome to this session of the Mosaic3DX conference organized by the Cambridge Games Creator. Can you hear me okay? Yeah?
Yeah.
Okay. This session is entitled Where Does the UK Stand in High Performance Computing? I'm Sasha Kostulovic. I'm the lead research engineer at Audio Analytic. What we do at Audio Analytic is a startup based in Cambridge. We do a new type of algorithms to recognize sounds for security applications. So we recognize gunshots, aggressions, car alarms, all those sorts of things. And the paradigm we're using, I mean the type of algorithms we're using are part of what's called machine learning. So we record thousands and thousands of sounds which are examples of what we're trying to recognize. We crunch them in big computers. That's our connection to high performance computing. And then the computers help us to learn from the data the parameters of the sounds that we are recognizing in our applications. There's something that's probably more my generation than yours, but there used to be that movie War Games where you had that supercomputer which was belonging, I think, to the US Department of Defense, something like that, and that computer was in charge of the managing nuclear war exercises and went mad and started nuclear war and so on, and ended up at the end of the movie playing tic-tac-toe. I'm sure that nowadays, about 30, 40 years later, supercomputers are still big cupboards with lots of blinking LEDs, but I'm sure they can do a lot more than playing tic-tac-toe. So to tell us more about the current state of high-performance computing in the UK and in Europe in general, we have a panel of experts today. We have Mark Hayes, the director of the Center for Scientific Computing of the Department of Physics of the University of Cambridge. If you could wave so that people know, I don't think I can read your badge from that distance. Then we have Dr. Alan Gray, research architect at the EPCC Supercomputing Center of the University of Edinburgh. And then we have Professor Dimitris Dikakis, the head of the Department of Physics of the Cranfield University. Thank you for accepting the invitation to come to talk to this during this session. I'm going to ask you to present yourselves in about 2 minutes. So, Mark.
Okay, this is on. Yeah, good. So, I'm Mark Hayes. I'm one of the directors of the Centre for Scientific Computing, which is based at the Cavendish Laboratory here in Cambridge. So my group grew out of the eScience programme, which ran in the UK for about the last 10 years, which originally was based on grid computing, sort of distributed HPC, but also with visualization strands to it, and some concept of how humans would work together in a distributed way. So lots of video conferencing technologies that we developed too. So that's evolved, of course. Grid computing itself has evolved into something that now might go under the name cloud computing. So we're still very much doing distributed computing, handling large amounts of data, and so on. The Centre for Scientific Computing itself is split into 3 parts. That's my group. There's another group that runs the HPC facility for the university, and another group that runs an MPhil course in scientific computing.
Okay, hello everybody, my name's Alan Gray. So I work at EPCC, which stands for Edinburgh Parallel Computing Centre, and it's a supercomputing centre within the University of Edinburgh. So it was first founded around more than 20 years ago now. It came out of the physics department. It's still part of the physics department. It grew out of the theoretical particle physics part of the physics department, which had a need for high performance computing. So they developed a centre to basically manage their HPC needs and their machines that they needed to use. Since then, EPCC has expanded. It now has around 70 staff, and it works on a wide range of different areas, not just physics, all different areas in science and engineering and industry, across a wide range of different HPC topics and projects. One of the main things that we do is we run the national UK high-performance computing facilities. For the last 6 years or so, we've managed Hector, which is a big machine, around 90,000 compute cores, which is based in Edinburgh, but is accessed by scientists, engineers and industry all throughout the UK. We're now in the process of installing the next system, which is called Archer, which is larger again, and it will be online soon. In terms of what I do, I'm a senior technical consultant and researcher involved in a range of different HPC projects, both management and technical work. One of my main areas of interest is using graphics processing units to do scientific calculations, so that may be of particular relevance for this conference. What we're finding now is that GPUs are emerging as one of the most powerful ways to be able to do these sorts of calculations, and the largest, one of the largest machines in the world, and the largest machine in the world until recently in the US actually basically gets its performance from using many GPUs, 18,000 GPUs in parallel, so that's one of my areas of interest.
Hello everyone, my name is Dimitris Derkatis. I'm the head of Engineering Science Division at Cranfield University. The division comprises 5 research centers ranging from several physical systems to fluid dynamics, aerospace, applied mechanics, and health engineering and related sciences. The division has about 100 members of staff and about 350 students, mainly MSc students and PhD students. My own research focuses on fluid dynamics and materials. I have over 20 years of experience in computational fluid dynamics and computational nanotechnology. And I have started actually using high-performance computing since the early 90s. At that time we had a transputer system, so we didn't have MPI and the libraries we currently use in HPC. I moved on to HPC using MPI and for a number of different codes ranging from computational fluid dynamics, fluid structure interaction, and materials modeling later on. Currently, my group uses facilities in the UK, the national HPC facilities, but also classified facilities at the Ministry of Defence. For example, AWU's facility in Aldermaston. We also use the PRESS High Performance Computing Facilities, which is the European Consortium for High Performance Computing, and we have access to some US facilities. So we have a quite broad experience in parallelization and use of scientific computing across a range of scales, from very small scales, nanoscales, to continuum scales, and also using a number of different computers, and hopefully we'll have the opportunity to talk more about it later on.
Absolutely. Right, so we're going to start with a very, very broad, very generic question. What is high-performance computing in general, and why it matters? Mark, do you want to start?
So what is high-performance computing? So, as distinct from desktop computing, I think would be a good comparison. So, as you will realize, your desktop computer and your laptop has a single CPU, perhaps a relatively modest amount of memory, and it's good for running a web browser, it's perhaps good for running games. If you're solving a large system of differential equations and doing some fluid dynamics, well, perhaps it's a little bit slow. And so a high-performance computer, perhaps if we're thinking in terms of definition, would have many CPUs connected through a high-speed network. Those CPUs themselves might these days have multiple cores. It would have the ability to handle large amounts of data and number crunching with that number of CPUs and a large amount of disk, therefore a larger amount of memory. So why it matters? Well, it matters to, first of all, who does it matter to? Obviously academics, modeling the world in mathematics and wanting to solve large systems of equations. It's going to matter to people doing fundamental research in that sense. It will matter to people like the Met Office. So the storm we had a couple of days ago was predicted several days in advance by a supercomputer, which was a lot better than we were able to do, back in 1987. it's important to people in the defense industry, for example, to model the way that atomic weapons might degrade over time. And doing those sorts of experiments in silico on a computer is a lot easier and a lot cheaper than doing them for real. And the same is true of medical simulations, for example. I'm involved in a couple of projects which are attempting to figure out better ways of treating cancer patients with radiotherapy, and being able to simulate treatments and being able to create artificial images and artificial tumors and figuring out how they work and simulating the whole sort of environment around those tumors is a perfect job for a supercomputer.
I'm going to ask the next question to Alan, actually. Are there different flavors of high-performance computing? You were talking about GPUs. Are there different types of architectures for high-performance computing which apply to different types of problems?
Yes, so the answer is yes, and I can try and describe them a little bit. So, in the past, you used to have actually a wide variety of different architectures, and in fact you would have scientists may decide that they want to design their own computer chip that's specific for their problem, so they would just go ahead and do that. And they could use, in terms of, as the previous answer mentioned, in terms of high performance computing, the idea is that you have lots of chips that operate together in parallel. But the problem more recently is that it basically costs a huge amount of money to create new chips. It's not feasible anymore for the high performance computing market to go ahead and design its own computer chips. It just costs too much money. The HPC market is actually relatively small compared to normal consumer markets. So what we're finding more recently is that the HPC market has had to piggyback on to consumer markets in order to make progress for a reasonable budget. So what we're finding basically is that you have traditional HPC systems will just use the same types of chips that you buy in your desktop PC from Intel, AMD, etc. And the main feature of HPC systems, as I say, is that they'll combine lots of these chips in the same system, and that means that they'll be packaged in a way that they're very densely packaged into servers so that you can get lots of chips in the same server, and the servers will be closely coupled with each other through special high-performance interconnects. And what I also mentioned previously was things like GPUs. So this is another consumer market, the computer gaming market, which is absolutely enormous, and it has driven the development of GPUs for the purpose of displaying graphics. It turns out that GPUs can be used for things other than displaying graphics, and they can be used for scientific computing. So as I say, what we're finding now is that some supercomputers are using GPUs as compute accelerators, so they go alongside CPUs in systems, and they can be used to accelerate certain parts of the calculation to make the calculation as a whole go faster. And that is proving very effective for certain types of calculations. But due to the nature of the architecture, there are other types of calculations that are finding it very hard to utilize GPUs. So we'll find that perhaps with a lot of work we can get these applications also running well on GPUs, or perhaps they'll continue just to use more traditional CPUs.
Okay. We're mostly talking about types of CPUs versus GPUs. Are there any other salient differences between different HPC architectures across different centers?
Well, what do you mean?
That might be a completely naive question. I mean, if I have to choose a high-performance computing center to solve my problem, what are the things I need to be aware of in terms of differences between your computing center, Mark's computing center, and so on?
Okay, so I guess there's, assuming that, obviously the main difference that I mentioned previously is whether or not GPUs would be involved. Assuming that they're not involved, then you'll probably find that different computing centers use similar chips as the kind of at the heart of those systems, I say either AMD or Intel. And then the differences will be in terms of how these chips, what sort of servers that they are found in and how the servers are connected. So, I mean, it's up to the buyer of these systems how much memory they would want to put in the server. Different application areas have different memory requirements, so you may find that some people would want to spend more on having larger memory spaces available for their calculations. And then, in terms of running large-scale, high-performance computing facilities, if you want to solve a problem using many chips in parallel, then you need to have a very high-performing interconnect, and that's where one of the major costs can come. So you'll find that some centres will, spend money on having very high-quality interconnects so that the different chips can talk to each other very quickly, whereas some other centres will use much cheaper, lower-performance interconnects. Perhaps that's not a problem for them if their calculations don't involve so much communication across processes. That's the main thing, I think.
All right, good. So talking about comparisons, Dimitris, you've been also one of the founding directors of the Cyprus Institute. How does the UK compare to other countries in terms of high-performance computing?
Yeah, I think this is a very interesting question because the UK does not produce the hardware, the HPC hardware, and this is actually one of the main differences between the UK and the US. So the market here is mainly we consume HPC resource that we purchase from other countries, mainly from the US. So in terms of usage of high-performance computing, I think we do very well. We have a very big user community across science and engineering. We have industry that are increasingly engaged in HPC and they want to support the parallelization, the development of new codes. In terms of how we do across Europe and compare the UK across Europe, I think we have the National HPC Centre that supports a large number of activities in the UK, especially the academic community. We also have other centres in Europe, like in Jülich and other centres in France. And of course the High Performance Computing Consortium in Europe, the PRAISE Consortium, which brings HPC resources across Europe, is a new initiative, a relatively new initiative, that brings together a large computing resource across the continent. Now, in terms of how we compare, if we take into account, for example, how many codes we use and how many users we have, I think there are a number of challenges. I don't know if you want me to elaborate now on the challenges.
Sure.
One of the biggest challenges I see myself in my own domain of research, which is engineering, fluid dynamics, materials, is that we don't have community codes. So what needs to be done there is perhaps to look at the possibility to have more collaborative work across scientific computing centers, across universities, and also bring industry closer to the centers. I would say, if I want to use in simple terms to classify where we are compared to Germany, for example, we are more selfish to develop our own software and pursue our own activities because historically we're more entrepreneurs in terms of the development of software in the UK, taking into account that most of the commercial codes, computational fluid dynamics codes or other codes have been developed in UK universities and then became major companies.
So precisely, when you talk about software, are you speaking about software for a specific application, fluid dynamics, materials and stuff, or are you talking about software for infrastructure, things like MPC, MPI and so on?
I'm talking application software in various domains. In the physics community, I think that more well streamlined there in terms of how they can produce community software, but the engineering community is slightly different. I mean, different groups have their own codes, they develop their own codes. In Germany and in France, there is more collaboration in terms of developing community codes, in addition, of course, to the individual codes that individual groups may use. And there are a number of challenges, of course, if we don't develop community codes, because it's very difficult to maintain, it's very difficult to re-engineer the software. For example, if you want to go from MPI to classical distributed memory computing to go to GPUs, then you have to re-engineer the software. And if you have a legacy code, this is a very difficult task. This is where industry has to be brought in and collaborate with universities. There are legacy codes in industry. I collaborate with a number of industrial companies, and And we have seen that it's nearly impossible actually to change the codes, because some of the codes were developed in the 70s. The developers of the codes have passed away, some of them, and you don't even know actually what some subroutines may do. So there are a number of challenges there if you don't collaborate together, universities, and try to produce actually common platforms with respect to specific applications.
So what's the dynamics at the moment? Is more towards a wider collaboration between computing centers, or is it still seen as a bit of a competitive advantage? Or my country has this computational facility, yours doesn't, something like that. Where do we stand in that?
I think we're more competitive. There is more competition within the UK between university groups and research centers than perhaps you find in other continental European countries. And my experience from the US as well, because I commissioned actually the job to establish a high-performance computing center in the southeast of Europe on behalf of the University of Illinois at Urbana-Champaign, that they run one of the biggest HPC facilities in the world. I think that also in the US now they try to bring together codes and establish community codes. In the UK we are lagging behind actually doing that.
Yeah, sure, Mark.
So Dimitris is absolutely right to highlight the importance of software in HPC. Now that Moore's law is kind of slowing down and leveling off, which means that the hardware isn't really getting much faster in itself these days, we need to think smarter about the software and the codes we're writing to optimize them. And perhaps the UK is a little bit behind the curve compared to, say, the ASCII program in the US in terms of the funding and resources available to build communities around particular codes and to develop software. Having said that, the government invested £40 million earlier this year in something called the Hartree Centre at Daresbury up in the northwest of the country. And their mission is to do exactly this, to focus on software supporting HPC and building communities, including links with industry.
Yeah, so I would say that I fully agree that one of the main challenges is software rather than hardware going forward, and the previous speakers were absolutely correct. I think there's also one of the main problems that's causing this is a cultural problem within universities. So as Dimitri said, a lot of codes, in our centre we see a lot of applications that come into us that are being used in research, and the typical procedure for developing codes is that you'll have a postdoc, a researcher that's a short-term position at university that will develop a certain part of the code while he's there or she's there to do specific functionality for their thesis or their papers. And then they'll move on, that expertise will be lost, someone else will come in and hack the code a bit more. And these codes have been developed over decades, and they're now at the point where, as the speaker said, that perhaps nobody understands what these codes are doing in full, they're just using them. So they're obviously not, and a lot of codes are not in a good state. And one of the main problems is that it's not seen to be a viable career path within academia to be an expert in software. Don't get me wrong, there are many experts in software in academia, but these are people who happen to also be experts in the scientific area. But I think we're getting to a point now where things have become so complex that within universities you need to have experts in software alongside experts in science to collaborate together. And at the moment the structure of research groups in universities doesn't allow that. There's no obvious career path for someone to develop as an expert in software within a scientific group, etc. And that's something I think that has to be addressed going forward.
Okay. So that to a large extent is going to depend on the users also pushing to have those kind of collaborations. And so let's focus back on the users. Maybe Mark, you were talking about all these various applications that are being developed and put in practice in the high performance centers. So can you just do again that kind of panorama, but maybe more from the angle of what types of problems we know about the applications, medicine, graphics and so on, but is it that behind these applications there is a type of mathematical problem that is better solved by using high performance computing?
There are sort of, in scientific computing there are two broad classes of problem. there are so-called embarrassingly parallel problems, which split into perhaps many chunks, many pieces that can be run independently, and there's very little need for communication between those pieces of code. So an example of that, a simple example would be factorizing a large number into its prime numbers. You can do that in a sort of brute force method and distribute the problem across many CPUs, and that's exactly what grid computing was good at. High performance computing, a slightly different problem. If you're solving a differential equation, for example, then you're typically using a system perhaps called NPI, and there's lots of communication going on between the multiple CPUs that you've split the problem across, and therefore, as has been alluded to earlier, you need a high performance, that is particularly low latency network between the nodes that form your high performance machine. And those sorts of problems are generally classed as high performance as opposed to high throughput computing problems, which is the former.
Okay. So those problems, the people who come to you with those problems to solve, are they mostly academics or private companies, or a mix of both? Maybe all three of you can answer that question with types of users.
Certainly academics in my sphere.
Yeah, so just to kind of elaborate a little bit, so I guess that taking a step back, if you go back 50, 100 years ago, then you would find that in terms of progressed science, there was two main activities, or two main pillars of science, you could say, and that was, one of them was performing experiments, and the other one was doing theoretical calculations. And that was enough in order to make progress in science and to gain new understanding, because the problems that were being addressed, you could you could do experiments to try and understand them, you could write down equations to try and understand them, and you could combine those two to gain a full understanding, and then you could develop your equations such that they'd match the experiment, and your understanding of the world improves. But in the last few decades, we've got to the point where it's just simply not possible to do this anymore, just using these two techniques, because the problems that we're trying to solve have become too complex, or are looking at scales that are far too small in order to do experiments, or far too large in order to do experiments. For example, one of the main things that cosmologists are looking at is how to describe the evolution of the universe. How has the universe evolved to where it is today? Obviously you can't perform experiments on the whole universe, so what do? Well, the only way in order to make progress there is to use simulation, to take your postulated theories and turn them into a computer program, and then evolve them in the computer program and find out what happens, and see how closely your evolved system looks to the universe as we observe it today. That's just one example, but that is the case across the whole different range of sciences, physics, chemistry, etc., astronomy. And we're now at the point where we need to use simulation in order to make progress. And it turns out that many of these simulations are just far too computation intensive to run on single desktop computers. So to answer the question more precisely, we have users from the whole range of science, from every different area in science, that have problems that they need to use high performance computing for. In terms of the balance between science and industry, it's far more weighted towards science or academia at the moment, but we do have a certain fraction of our users coming from industry, and I think that will increase as time goes on, as industry realises that it can actually become more productive by having their models run faster using HPC techniques, etc.
I think if I can say a few words about industry, because of my involvement with a range of engineering industries in the last 20 years, I think engineering industry still doesn't have the time and the resources in general to invest in HPC. They may, depending of course on the industrial sector and the broadness of the use of computing within the sector, You may find some industries, of course, to have purchased HPC facilities, but they don't have their own experts to parallelize existing codes. So they mainly rely on commercial software or on academic software that is already parallelized by academic users. So HPC for engineering industry is not the aim. Provides the means to produce results and reduce the turnaround time actually of obtaining the results in order to design and optimize the design of the product. So this, my experience is and my feeling that this is going to continue for a while unless of course the use of HPC facilities and the parallelization of existing industrial codes becomes easier and easier. The other thing is the cost that many companies, especially SMEs, but also larger enterprises, they don't have the money to invest every 3 to 5 years to change the HPC facilities. We have to take into account HPC facilities, and I hope my colleagues will agree, are consumables. You don't pay, you buy a car for 7 years, 8 years. A HPC facility will not last more than 3 to 5 years. You have to change the hardware. And the technology changes, and then of course you have to optimize the software every time you make changes to the software as well. So it is a different kind of thing actually, HPC for industry, HPC for academia. As far as academia is concerned, if I can say a couple of things about the software challenge there again, is that I fully agree with Alan that we need to have experts in software engineering within academia in order to maintain actually the level of development in HPC. Software becomes increasingly more complex. The facilities and the hardware, like GPUs for example, requires additional software experience and skills. Therefore, we need to invest in academia to employ software engineers who are going to do, to be, in other words, the gatekeepers, well, or the custodians, if you like, is the right word, the custodians of the code developments in order to maintain the HPC software, scientific software development.
So it's no big secret that scientists in general don't make good software engineers. But why is that? Well, you know, it's not the scientist's job really to be a good software engineer. They're mainly focused on the scientific outputs, and if their code runs perhaps twice as long as it needs to, well, that's not a big deal so long as they get a paper out of it at the end of the day. But of course, Alan spoke earlier about the twin sort of tracks of science that we've had historically with experiment and theory. And it's always been the case, of course, in science that if somebody runs an experiment, that ought to be reproducible. Somebody ought to be able to independently run that experiment and verify that what you've said is true. Well, now as more science is being done on computers, this becomes harder. Although a scientist will publish a paper, it's pretty rare for the code behind the results that they've published to also be released. And so the possibilities for reproducing that research are very much diminished, and there's a problem here, and it's going to get worse. You know, as time goes on and as computing becomes more important in science.
But some teams do release their code.
They certainly do.
It's coming literally. Yes. I mean, I've seen that appearing in speech synthesis or speech recognition, like people releasing codes more and more. So is there what's the trend at the moment? Are more people being aware that it's important to publish the code as well?
Yes, but it's happening slowly, more slowly than it needs to, perhaps.
Yeah, so that's absolutely true. And there does seem to be more pressure from the funding councils who are giving money for the research, that if they're giving money, that one of the conditions that they fund is that the software will be made open source, made available for anyone to use and to inspect. But I guess there's a difference in the sense that when scientists release a paper, then it has to go through a peer review process, which means that it's given to other academics to review it and to decide whether it's acceptable quality to be published or not. And at the moment, there's really no process for software at the same. You know, if someone's results are underpinned by a certain software application, then there's no process for that software to be peer reviewed and to become part of this process, and that could be one of the main reasons that, or one of the main problems going forward, has been said, that if more research is underpinned by software, how do we judge the quality of the software that is being used to create these results? The reviewers have no way of knowing if the software is giving the right answers or not.
So these considerations apply to academic work, but you see also some private uses of your high-performance computing facilities, in which case releasing the code would be a bit more difficult. But like, do you have lots of private users, and do they see it as a cost or as a benefit to use high-performance computing?
So in terms of industrial users, well, taking a little bit of a step back, I think it's now been, it's been realised at the highest levels of government that high-performance computing is a key area for the UK economy in terms of underpinning knowledge within the economy, and it's seen as one of the foundations of that has to be provided for in order for the economy as a whole to grow. But more generally, in terms of what we see on our systems, in terms of industrial risk, I mean, so you have the fact that science itself underpins the economy, that science going forward will then lead to new ideas and new companies, etc. And as I say, high-performance computing is one of the key areas that's required by science. But you do also have industry directly using high-performance computing itself. One initiative that we've been involved in relatively recently is that the Scottish Government has funded within Edinburgh a project for us to work with a large number of Scottish small SMEs in order to first of all, to do evaluations of their processes to see whether and where HPC would benefit them. So this is all paid for by the Scottish Government rather than the companies. And then there's a second stage where a selection of those companies are chosen to go through in order to perform actual work for them, to develop software that they can use within their companies and run this software on our HPC systems. And I'm sure as that progresses, that will lead to more longer-term collaborations between our centre and these companies to the benefit of both. We have had collaborations with a number of companies over the years as well outside of this, and these have been very positive.
Okay. Talking about access to high-performance computing, so if you're an academic or a company, to begin with, what kind of homework do you need to do to determine if your problem might benefit from high-performance computing?
So what we typically find is that in terms of academia, then obviously academics will be working within a research department in a university. Most universities have their own HPC facilities, smaller scale HPC facilities than what obviously the national HPC facility. And so what we'll find is that typically users will experiment on these smaller scale facilities, and they will run their software on these, and if that satisfies them, then that's fine. If they get to the point where they really find they can't do what they want to do using these facilities, then that's the point where they'll step up to the national facility. And the process for doing that is that they will typically they'll write a research grant proposal to one of the funding councils, and in that grant proposal they'll include a certain amount of money to be spent on accessing our facilities. So that's one of the mechanisms. We also recognise the fact that not everybody has reasonable sized facilities. So we do have certain funding calls that we issue directly that allows people to come on our systems for a relatively short period of time, 6 months or so, in order to do experiments and get themselves ready to then produce a funding proposal to get larger amounts of time on the system.
Okay. Mark or Dimitris, do you want to expand on this? So we've talked about applying for grants. Are there other pathways to use the high-performance computing facilities in the UK? Can you just turn up and say, okay, can I use your facility if I pay you X? Or are there other types of mechanisms you have to go through to have access to high-performance computing facilities?
Well, as far as academia is concerned, I mean, many universities now have their own HPC facilities. Of course, the scale of these facilities compared to the national HPC is much smaller, but you can access the facility, and depending on the university, there may be specific procedures, internal procedures, how you apply to use the HPC facilities. At Cranfield, for example, we don't have a system to charge the computing time actually spent on the facility. So, because we're a postgraduate university, the PhD and MSc students can easily access the facility. Other universities may have a different system. To use the national HPC or the European HPC resources, you have to go through an application process. And Alan is, and of course the group here are very familiar with this. You have to apply through EPSRC, the Engineering Physics and Research Council, and or other BBSMC, the Biological Science Research Council. And then when you submit your application, you can also submit an application for HPC resources. Another way is, of course, to establish or participate in consortia, which are HPC consortia, and there are a few HPC consortia specifically focusing on applications, different applications, and then the consortia can apply as a group to request resources, HPC resources from the national facility. There may be other ways to secure HPC resources if you collaborate with a specific customer who also has a large HPC facility. For example, I personally collaborate with MOD, and in the framework of this collaboration, we can access MOD HPC facilities, which are classified, of course, and from time to time you may need to have people who have clearance to access these facilities. I don't think it is straightforward to use US HPC facilities, isn't it?
Well, first of all, I'll just make a point to do with our facilities that we actually do allow access, sort of pay-as-you-go access for industry as well. We own a small percentage of the system ourselves rather than sort of leasing it to the UK community, and with that we do offer that to industry. You just have to get in touch. They can pay money and use the facility. We also have another machine, a smaller scale machine that's just private to EPCC, but we, again, the name of that machine is Indy, which is it's called that because the idea is to collaborate with industry, and again that can be used by industry for a reasonable cost. So in terms of using facilities abroad, within the US, the US have mechanisms, and I'm actually using a US machine at the moment. There's a program called Insight where you can, if you have a research proposal, you can apply to this program and they can grant access anywhere in the world. So that actually works very well. And as already been mentioned, within Europe there's the PRACE infrastructure where academics in one country can use a machine in a different European country, and there's, throughout the year there's different mechanisms for people to apply to do that as well.
All right, thank you very much. Did you want to? Yeah.
So there's one other route which we should. You can rent CPU time these days, of course, by the hour from the likes of Amazon with cloud computing. I don't believe that the more expensive and high performance interconnects are available on the Amazon HPC.
They do have now.
They do now.
They do have some, yeah.
Right. You can also rent time on GPUs from Amazon, of course. Getting large amounts of data in and out can be a problem. Although Amazon have the facility to physically ship hard drives into their data centers. Of course, all you need to get started is a credit card, and you can be up and running with a reasonable sort of sized HPC facility of your own within a few minutes, although paying for that in an academic environment is not always straightforward.
Okay, thank you very much. We have like 2 minutes to conclude before the questions. So we've made that panorama of high performance computing in the UK, which can solve all these diversity of applications. We said there is that call for more collaborations, more sharing of the code, more clearly defined track to becoming one of these high-performance computing engineers. Is there any final points that you guys would like to make about high-performance computing?
So Yeah, I guess just to reiterate, I think one of the main issues is going forward is software. I think the hardware provision is kind of taken care for, and that the main challenges going forward will be to create efficient software on these machines. And actually, the main issue is creating codes that will perform well and not take a lot of power, because power is becoming, in terms of hardware, power utilization is the major issue going forward, and we're seeing that's one of the reasons why we're seeing increasing use of GPUs, is that these have a very high power efficiency compared to CPUs. But the problem with that is that it's harder to use GPUs. GPUs typically have hundreds of thousands of cores on them compared to having just maybe 8, 12 cores on your high-end CPUs at the moment. So you're getting your higher power efficiency through higher levels of parallelism, using hundreds rather than a few cores. And that has an impact on software. It means that you have to do a lot more work within your software in order to realise that performance. So I think the situation with software at the moment is not ideal, but it's going to become a lot worse in the future. And you said that exactly the what we need is more collaboration. For example, EPCC, we've been doing parallel computing for a long time, and we're always very keen to set up new collaborations with all different areas of academia, industry, etc., where we can lend our expertise in parallel computing to solve any different type of problem that people have. So people, please feel free to get in touch if there's anything that we can work together on.
Dimitris?
I'd like to just point out a couple of other challenges, which is, in addition to parallelization, which is the data processing. Excuse me. I think one of the biggest challenges in engineering applications, at least I think the same is in science applications, is the proliferation of data. We can easily, for example, for problems like turbulence and direct numerical simulation of turbulence and complex law physics, you can produce very huge amounts of data within a relatively short period of time. And then the computation may be for a couple of weeks, and the processing time we need may be several weeks or months sometimes. So how we manage data becomes increasingly a very big issue. The other thing is education. I think we need to invest into the education aspect of HPC. Software engineering education and other software education in general, because the universities at the undergraduate level are not very good actually at providing the modules that researchers and scientists who, and engineers who are going to use HPC in the future need to know. And I think we need to have a compulsory kind of way at the PhD level, those who do actual scientific computing, not to become blind users of software that is provided to them, but have knowledge across the board of software engineering and scientific computing in order to appreciate actually the challenges and be able actually to produce and use the resources, produce data and use the resources in a way that is reasonable.
Mark, very quick final point before the questions.
So I'd just like to pick up on the training angle. We really do have a skills gap and a training gap in this country. And although there are sort of pockets of expertise, and there are master's level courses in scientific computing run at Cambridge and Warwick and Edinburgh and so on, we're educating hundreds of students a year perhaps, and the courses are always full. And we need to get from there to educating thousands of students per year. How we do that is an open question.
About 10 minutes for questions.
Hi, I have a long-standing interest in a theory called CSP by Tony Hall, and there's a conference series called Communication Process Architectures, which focuses on that theory. I was wondering whether there's anything in the HPC world which can benefit from that, and particularly some of the challenges and successes. I admit there are some failures too, but of the transputer from the 1980s.
Sorry, I missed the question. Could you just repeat it from the first part?
So the process theory, communicating process architectures conference does. The CSP is a theory from Tony Hoare, developed 1979, 1983 era. Tony, I believe, works here. I'm not sure. Anyway. That theory is basically that you can break down a program into an arbitrary number of processes. That the current OO way of doing things with classes and so forth is one way, but not the only way of breaking down a process.
Yeah. So,
and basically, I'm saying, are there any things that the HPC world can learn from that?
Yeah, I think one of the things you touch on is one of the major problems going forward is that as I mentioned earlier, you say the idea is that you want to break down a process into a number of as many different parallel parts as possible, and that is the key thing that we have to do going forward. As I mentioned earlier, in order to make progress, we have to exploit parallelism. We have to decompose our problems as far as we physically can, or we possibly can, in order to identify the different parts of the problem that don't depend on each other, so that these can be scheduled to happen at the same time as each other on parallel hardware, whether this be different cores within a chip or whether this be different chips. And that is one of the key things, and it's a very hard thing to do, and because parallel programming is hard. I mean, even though our brains are actually parallel computers, we actually find it very difficult to think in terms of parallel programming, and naturally we like to think in terms of sequential serial programming, but we have to just force ourselves to think in terms of how do we break a problem down into as many different parallel parts as possible, and assign these across a machine.
Sorry, can I actually say, if you talk to a hardware engineer in electronic hardware, you will find that they naturally think parallel. The theory that parallel programming is hard is wrong. I'm sorry to disagree, but it is wrong. The point is that we've been taught to think sequentially.
Okay,
and that those who are taught to think in parallel find it easy.
Okay, I'm going to disagree with you there, I'm afraid.
Just bouncing out, that's probably an instance where joint work between an HPC engineer and a user would be fruitful, because you coming with a new problem, maybe those guys haven't heard about it before, they have the expertise to parallelize it, to break it down and organize it in those fantastic computers in a way that's going to benefit you. So probably bouncing on what we said before, I mean, also from my own experience at Audio Analytic and other positions I've held before, the best teams were the teams where a researcher was teamed with an engineer, and where the engineer was doing all the work of computer, like software design and organizing the scientific problem into a computer program, where the scientist was more on the theoretical side of things stuff. So that's probably where users need to do a bit of homework, but also be paired and have some ongoing communication with the HPC engineers to get the most benefit of these high-performance computing facilities. Do we have any other question? Maybe, sorry, just the same, or just, yeah, here.
Hey, thanks for the presentation. I work in Cambridge at Cavendish Lab with a group that does quantum mechanical simulation, and we have a sizable code, and I get the impression that which is run on lots of different supercomputers by different groups who distribute this code, like the Blue Gene computers in the Hartree Center, or in the national labs in the States, or the Intel-based supercomputer in Cambridge. And I get the impression that to take full advantage of these supercomputers, we need to write lots of compiler-specific optimizations within the code, and that's not really something that, as a research group, we have a capacity to do. We don't have like you said, we don't have the manpower or the really the willingness at the moment to do this. Do you see this changing in the future? So I guess a more uniform set of optimizations across different compilers and different architectures.
My answer would be yes, I hope so. And part of the way we get there is obviously training, but also developing the tools. Kind of back at the previous question, perhaps, in theory, thinking in parallel is easy. In practice, the tools we've got for parallel computing are hard to use. Right? Yeah.
So I guess this touches on a point I made earlier that we really need experts in this within groups that can do this sort of thing. But also, I think that it's possible to write codes in a certain way that the compilers have more ability to automatically perform these optimizations themselves, which avoids the need for you to do compiler-specific optimization.
One very last question, very quick, if you can, just a gentleman there.
Hi, my name is Gareth, I work in video games. We do parallel programming, and it's incredibly hard to make something complicated efficient. It sounds like you're struggling with trying to teach scientists to program as well as do their scientific side. Have you looked at any ways where you can visualize the processes and remove the bulk of all the communication and the data transfer and the dependencies and bandwidth, and let them concentrate just on the key areas and take away a lot of the programming parts away from them? Do you understand what I mean?
Yeah, it's a hard one because basically you can do that sort of thing and allow people to program at a higher level, if you like, so that they can concentrate on the science, and then there'll be some way of automatically taking care of the code generation. But the problem is that the higher level you get to, the less scope you've got for optimization, and the slower your code is going to run. So there's a real compromise there.
It's more just the communication, the data transfer, the dependencies.
Well, you always want to minimise these things, but there's going to be some inherent level that there will be there. So yeah, you really need to minimise these. But people are better at doing this than computers because people are smarter than computers. So you really have to have somebody looking at it and understanding it rather than relying on a machine to do it automatically at the moment anyway.
All right, thank you very much everyone for attending this session. Let's thank our speakers as well. And, please stay in the room. I think Ramin Zehi has an announcement to make. Thank you very much.
Hello ladies and gentlemen, thanks for coming today. I'm very grateful to everyone here, seeing so many people.